Yeah, so welcome to the last talk of this conference, hopefully not the least. I'm Martin Held. I work as a data scientist for Finleap, which is a company builder in Berlin. So we build fintech companies from the very early stage, and Finleap does early investments into these ventures and supports them with like central functions, marketing, HR, tech, accounting. Here's a kind of little overview of the companies Finleap already built. And one of the most remarkable ones, I think, is Solaris Bank, which is a fully licensed German bank, which, with the help of Finleap, was able to acquire a full bank license within just 9 months' time, which I think has been set a new record in the industry. And they're going to set out providing API banking, actually, for fintech startups. So I work in the tech department there, in the central, like in the incubator in Finleap. And we usually, from the very beginning of the venture, have a quite strong kind of impact on the early build kind of startups and ventures. And so we tech and product support them in actually building up the initial tech prototype, or the program, actually the services the venture delivers. Support them actually building up the initial team and coaching them in like technical questions and product questions as well. So over time then the responsibility of the central tech and product team reduces, and the ventures themselves actually build up their staff and their processes and everything. So with this experience in mind, I'm now going to talk about this kind of journey we had on the tech side and how we actually started building like products or services in the tech team, and then over time actually learned from that and eventually arrived at the kind of current kind of architectural pattern we use. And I will also actually look into why this is actually interesting also for data scientists doing it this way. So initially, when we started kind of supporting the ventures in the early days, we usually started with building like a minimal viable product, a prototype, using a kind of monolithic application architecture. That means all the components we have in the product are sitting tightly together in one big kind of block. And for example, if you think of a web application, usually you have some user interface in there, you have some backend that communicates with the database, you have maybe multiple services that send out messages to clients or query external API services to get some data in. And you also usually share some data in that. And so initially we did this mainly on Ruby on Rails, which is a nice framework to actually do things in a prototypic way, to actually achieve results really fast. And we went quite good with that in the beginning, but over time we realized that there are some kind of shortcomings with that as well. So I think finding developers is not only in Berlin, but I think probably almost everywhere quite a hard thing, finding good developers. But if you constrain yourself to a specific tech stack, say Ruby on Rails, and you only are able to hire in this kind of domain, it's even harder, right? So you prune down your kind of hiring space quite a bit. If you say you're only specifically hiring only for one tech stack, then if it comes to data science, particularly with Ruby on Rails, there are not that many kind of number crunching libraries available. So in order to actually get some data science into the product, you would need to actually think of, okay, how do I do this? How do I call external services and how to integrate them? It can get quite messy, so it's not straightforward. And then if the ventures start to actually lift off and grow, usually demand is also likely to grow for the application, and you might need to actually scale it, be able to scale it up a bit. But if you have this kind of large code block structure, it's pretty can be pretty cumbersome actually to achieve scaling there of the components, because they are all living in one big kind of maybe code base. And also it's not sometimes really hard to figure out what are the bottleneck in the application is. So over time, we then learned, or we actually started to investigate a little bit into this very kind of now popular microservice pattern. And this, the idea of that is actually quite straightforward. So it just says all the components we've seen in this monolithic kind of single application, we split up into individual services that are loosely coupled with each other. So the services can talk to each other either directly via some APIs or via a message bus, say, or message broker. And that way, it looks a bit more complex in terms of communication that goes on, but it actually has a lot of advantages. that comes with this kind of architecture. So we started to actually look at that and actually rip these things apart in actually individual services in order to be able to actually overcome these shortcomings I just mentioned. And in a minute, I will talk about Dockerizing, so about containers. So the services, they come with this little kind of logo in the background. That means that they're in a Docker container. What that is, I will just explain in a minute. But just keep in mind that these services are containerized services that can be used in this type of architecture. So using these kind of microservice architecture comes with some very nice properties. For example, beforehand we were constrained on this kind of Ruby on Rails, or you name it, maybe Java stack. When you actually rip the services apart, you can really have multilingual applications, meaning that every service you use or you make use of in the whole application, you can be implemented in a different kind of language. And if you imagine as a company builder, or maybe also in a different kind of environment in an organization, you usually have like people with different kind of development backgrounds, and everyone has maybe their kind of pet language they wanted to use best. So if you rip these services apart, you can really distribute also your resources, like development resources, better than the ones who like to, I don't know, use Elixir or Java or whatever, can actually implement a service in their particular favorite language. And then you put it into the architecture and it integrates well with the other components if you specify the interfaces correctly. So this opens up the talent pool for recruiting, because you don't constrain yourself to a specific technology, but you rather look for people that kind of are capable of understanding the architectural pattern and can actually code for these kind of service interfaces, which I think it's quite advantageous. And also if you think now of, in terms of data science, so you might have actually very specific data science library you want to use, or very specific kind of tooling there, for example R or so, which has not really been made to be applicable in the modern web tech business, I'd say. You can, if you containerize these things into a container and make this architecture that it's kind of interplays well with other services, actually more easily plug in data science services. And as far as scaling is concerned, you can, of course, then figure out, okay, which of the building blocks of your kind of system is the bottleneck, and try to scale that up in the best case, let's say like this. And also from a business perspective, this is kind of has neat properties, because if you think of now the services get more, individual services get more complex maybe, or get more services, you can also build your development teams around services, and then scale the team with the complexity maybe of the service, or actually put different services on different teams easily. And from a company builder perspective, of course, if you once develop maybe something like an authentication service or something like that, this can be more easily reused for other projects, I would say, as if you would actually have a large code base and you then just put out maybe a bit of the library and stuff like this. So it permits also reuse of services. So now I mentioned these kind of Docker container concepts. I think that they're quite popular now in the general like software world and also DevOps world, but in the data science community, I think they're not that kind of commonly used yet. Maybe it will actually lift off in the future. So just to give you a little bit of an idea what that is. So it's nothing more than a kind of a nice package of code, basically. So it allows you to package up your application you wrote, including all the dependencies this application might have, so libraries, for example, into one container. And then once you have a machine that has a Docker kind of engine running there, you can deploy your container there, and it will actually just run without actually modifying the machine installation or modifying the environment of the machine. Yeah? And so it's quite neat to package up things and deploy it anywhere where you have a Docker engine running. Yeah, some of you might be actually familiar with virtual machines, which kind of it's more heavy a concept of having a separated kind of virtual environment on an operating system. Docker containers differ from that in a way that they share their the underlying operating system resources. And so this way they are more lightweight, so you don't boot up a whole virtual operating system, but they actually live on the existing operating system, making that much more easy to start up and more lightweight in terms of memory footprint, for example. So what is actually, how would life in the data scientist container look like? So why is it also relevant, in my opinion, for data scientists? because you can actually package very complex things into one container, then use the container, distribute the container, deploy the container to production. And yeah, you don't read this text. Basically, it tells you just the commands and or definitions how you actually build up this kind of container by specifying what libraries to be installed. It's basically, you can think of like a shell script kind of thing where it tells you, okay, you start off with something and then install. So can get quite lengthy. And just this different representation of what we just have seen. So you start off with some basic container you use as a kind of parent. In this case, just an Ubuntu installation, and then you install all dependencies you want to actually have in the container to be used. In this particular case, I will have an example in a minute. We built here a very reasonably sophisticated data science container that it's able to run a deep learning algorithm to actually solve a image classification problem. And so what we all put in there is like a Python, the Caffe deep learning library. We compile it from scratch into the container, and then we install for Python dependencies everything that's actually needed. We also add a pre-trained deep learning model and put everything in the container, and then you say build, and then this container is available, right? And you can, so your machine where you did this is still kind of in the state it was before. It's all happening in container. It still stays clean, and you have everything in there what you actually need to actually use this this complex kind of complex library, and with all the dependencies you have it in the container. So just a little example to see to show you how what can be done with that in a way. So what we did is we just built a data science container, what I just shown on the slide before, that does some image recognition. So the idea is you put in an image into the container, and then the container will actually give you the class labels of this image using this deep learning network as a pre-trained network. And in this case, it will tell you electric ray, cramfish, numpfish, or torpedo. And I also have a live demo here. I hope that I get it on the second screen. Unfortunately, what is happening? There we are. I'm not sure where you put actually the monitor here, but which direction do I have to go to come back? I lost my cursor. Okay, to the left. So imagine, now I'll show you the following. So this picture, I just scraped it from the web. It actually shows a Berlin kind of scenery. This is something now we put into the container by saying, oh, you already see the result. This is unfortunate. So we have a container here named data natives DNTLV, which contains all the libraries. I've just shown you the Caffe library, the neural network, everything is in there. And if it started, it looks into a certain directory and sees, okay, what are the images in the directory, and applies these kind of classification logic on that. And what I do, I just mount the current directory in the subfolder demo, which is just this folder that contains here this Berlin image, and starts up the whole kind of machinery in the container, loads the deep learning model, loads the image, does the classification, and then comes up with some labels. It's a little bit of a toy example, but I think it nicely shows the potential of this kind of technology, because this container I could just distribute to anybody, and it would work. So what's really interesting is, so there's a crane actually recognized. So there's some cranes. I mean, it's hard to tell by the eye almost, but there are some cranes. Then there's a Reichstag, which is classified as being a palace. Not too bad. Then there's a pole, which is probably the TV tower. And what the funny thing is, I guess the mosque is the Berlin Dome, I would assume. And yeah, flagpole is probably also the tower. So this is just to show you like a little bit of a toy example what you can do with building such a container thing. And now let's hope that goes back. Yeah. Yeah, so this was like using one container for like more or less sophisticated data science stuff to actually do image classification with the deep learning net. However, a single container is maybe nice for like playing around on a data science kind of workstation. But at some point, eventually, you want to actually bring it to production and actually come to a point where you are this kind of scenery where you have these microservices and actually serving some production or doing some productive things. So what you need for this is actually an orchestrator. So the orchestrator, in this case, it's a Kubernetes logo. That's what we also use in Finleap at the moment to do this kind of orchestration of different containers. So once you have your packaged up your code, your logic can be web server serving a website or whatever, or a data science thing. You want to actually have it running in your production environment or somewhere deployed, right? So how do you do that? And what's really nice about Orchestrators is they abstract away completely the notion of a machine. So you actually only have a kind of a cluster or an API endpoint where you can actually say, okay, behind this endpoint, there are just computational resources. I put the container there and then do whatever you want with it, but actually just keep it running and make it running. And there's a certain components you have to have in the orchestrator, so it does the scheduling, which is just looking, okay, which machine actually has enough resources to actually host the container in terms of memory and CPU requirements. If you have multiple containers running, they need to talk to each other and discover each other. So it also allows you to register the container under name and all these things, all these kind of things. And also what's really neat about that one is it implements like resilience very easily. So for example, if you have a problem or some process in the container dying, it implements resilience. So it just observes like a nanny if this container is kind of still alive. If not, it will restart it. How much time do I have left? Okay, cool. Yeah, so this is just, okay, you have containers. We have container orchestrators that allow us to actually deploy containers to production. And what can we do with that? And this is a project we initiated around last Christmas in Finleap because we had some spare time, I'd say. I did this with this gentleman sitting in the audience in the back. And so we came up with, okay, so now we have understood, or actually started playing around with containerization, with deep learning stuff, also with microservices. What can we do with it? And tested how actually, what complex architectures can be built with that in a quick way. And we just thought, okay, set out to actually have some fun with that stuff. And I don't know how, but we came up with an idea of building like a reverse image search using like a deep learning as feature extractor for the images. And probably I don't have to explain too much, but reverse image search just means you have a database of some images, in this case shoes, and you put in a query image of another shoe, and you want to actually see the shoes of your database that have a certain or the most similarity, are most similar to the one actually you put in. And we did that using, implemented that using the microservices and Dockerization approach within, I don't know, 2 or 3 weeks in a spare time, which is pretty nice. And just to walk you through a little bit through the architecture to see actually these concepts of the containers. So first we needed to create a database of images. How did we do that? We just went out to the internet, to a online shoe store, basically. And scraped their product descriptions and product pictures, basically, with a crawler service. So this is now like an individual service that runs there, crawling an online store, scraping basically the product pictures, in this case shoes, and also the raw metadata, which in this case just the HTML page surrounding these, or the HTML page of the shoe or the product. And so the service would constantly scrape from the internet pictures and raw metadata and put it on a message queue and a message broker where they would just reside. Then to this message broker, we actually connected other services that did something with the stuff actually coming from the crawler. So for example, one important component was the feature extractor service that took the raw picture from the broker that was scraped and extracted the features of the picture. Initially, or like classically, you would think of like, I don't know, extracting, I don't know, grayscale values, edges, and other things if we do an image recognition. Here we used the kind of deep learning net I showed before to actually not go down to the class labels, but one level above to actually have a high-level feature description of the objects on the image, and put these features, the extracted features, back to the message broker. And we wanted to actually have some nice showcase. So also we sort of, okay, when we have the similar shoes found, we also would like to actually or also like to show the price and the name of the shoe. So from the raw metadata, the HTML page, we would need to actually have a parser that parses out the structured, parses the data in order to return some structured metadata, price and name, for example, of the shoe. So we have a metadata parser service that does this trick based from the stuff that the crawler actually put in the message bus. And finally, we need to persist the data somewhere to actually be useful for other services as well. So we had a storage thing service that just took all the 3 things from the bus and puts it in a database. So then you want to actually have this kind of available to clients or to actually browse your data. So 2 other services necessary for that. One is a search API, which is just an API endpoint where the web app would connect to and send query pictures. And this guy would then take care of also extracting the features. It's not 100% correct. We would also use the feature extractor for that, but would extract the features from the query image and then send the features to a nearest neighbor service that would then go down to the database, look into, okay, which are the pictures I have in the database that have similar features, and then return a list of very similar pictures. This is how it can be done. Each of the blue boxes is an individual service, could be implemented in different different languages. I think here we had like Node.js, Python, Rails, and something else. I think 3 things. And if you figure, for example, that the feature extractor is rather slow if you compare it to the crawler, you could easily scale it up by just deploying more of those. Okay, I think I have to come to an end. And just for you guys to take home, so I think containers are a really great tool to package up code and all its dependencies and to make it usable by others and also deployable into production eventually. And from a data science perspective, I think it's cool because you can actually work in your data science world, I'd say, or bubble, and then develop your stuff in a container and just deploy the container to the rest of the kind of architecture, and it will do the trick. And with this open source, so it's all open source technologies, right? So Kubernetes and Docker, it's all open source, so it's for free. So I think, in my opinion, it really opens up the world of complex scalability and resilient services to the masses. Okay, thanks for your attention. And I'm not sure if you have